Alright, this is the last video, and this will just be an example. I'm going to start this here and see how it goes. Okay. So in the previous two videos, we talked about the equations for the Otto cycle and where they came from. And you might be wondering, why are we doing this if I'm never going to see it again in my life, or numbers that I'm getting are too high. I I know at this point, as I mentioned before, you guys you guys are great and you understand everything now, and this is just some applications, and I'm not going to say you're going to see it again because I'm a mechanical engineer and I didn't see this again until I started teaching this class. So I not this semester, but until I started teaching this class, like in my other classes or any projects that I did. And I just want you guys to understand that that doesn't matter. What we're learning here is how to solve a problem. We have some information that is known, and we have some tools that we've acquired and that we understand where they came from. And we want to learn, or we want to practice or get some experience with solving a problem. Doesn't matter what that problem is, okay? After you move on and you leave the class and you leave UF, you'll be solving other types of problems. Maybe you'll be a doctor, you'll be a lawyer, or you will go help people who need your help, and you'll be solving all sorts of different problems. Many of them not only not related to this class, but not related to anything you learned at UF. So it's not the subject itself or the problems themselves. Is learning how to solve these problems. And I know you guys know how to do it. So in this case, is being aware that you can solve these problems. And that makes a difference. You can solve any problem if you have the tools, and you can review those tools if you forgot, and you can just go out there and solve any problem that you encounter. And that's why we're doing this. Speaking of that, we're gonna solve a problem here. So, not sure now you're inspired. You're like, oh, I want to solve that problem. Probably not. Once you see the problem, we're gonna solve an Otto cycle, which here it says 934, and this is on your email. All right, and I don't know if that's 934 from the textbook. If it is, sometimes I change what I ask from the problem, so I don't know if you should look at it. I haven't looked at it in a while. So let's see what's given here. We have the compression ratio equal to 8, and we have that T1 is 300 Kelvin, and we have that P1 is 95 kilopascal, so something that's important here. Those are the lowest values. So that's one way that you might find out on your exam, or if you have to do this later. It may say the minimum values for temperature and pressure. If you go back and look at your TS and PV diagrams, you'll see that those are the minimum values before we do anything to your system, before we compress it and heat it up, okay? Those are given. We have Qin also given. We want to find the peak values, P3 and T3. Those are the maximum values. That's another way that I might ask it on your exam. And we want to find the net work out of the cycle, and that is work out minus work in, okay? Because yes, we're getting work out from 3 to 4, but we need work in order to accomplish this. And we want to find the thermal efficiency, okay? So let me see if I have time to solve two problems. The other problem I have here is 9.3. What I'm going to do is we're going to do that one on Wednesday of next week. Okay, so for now, we're just going to do this one. All right, and then I'm going to post two practice problems. One that I think is easier than this one, and you're going to solve it two ways, using air standard and cold air standard. Okay, so if you want to practice that for Wednesday, great. If you don't have time, it's fine, because then on Wednesday I'll probably post one or two more, and that's it. Like, that's all you need to solve for Friday after you've solved your isentropic problems for air. So just a quick comment. I don't know if I mentioned this before, but it will be on your study guide. Your exam number 5 has an auto cycle, and it also has that last suggested problem, the suggested problems that I posted, that they are on isentropic processes for ideal gases, but it also has entropy for ideal gases, because all of this is relevant, okay? And you have entropy for ideal gases here. So your exam might have generation of entropy for ideal gases, because everything accumulates, all right? And just change of entropy for ideal gases, and not just isentropic processes, okay? All right, so here we're solving for P3 and T3, and the first thing that we're going to do is figure out what equation to use, because if you look at this, all right, I already solved this, it's great, you know, it looks easy, but what did I do? You know, how did I figure out what equation to use? Because if you look here, air standard, and I'm doing this air standard because the problem doesn't say anything about cold air or using constant specific heat. If you look here, there are a bunch of places where we have T3. We have T3, well, you can't see this, but you have it. We have where we have constant volume from 2 to 3. T3 is there. When we have isentropic from 3 to 4, we can find T3 with BR3 or PR3. So some problems have the compression ratio, and you use that, okay? Actually, like the one we're going to do on Wednesday, that one has a compression ratio. You can use a compression ratio to go from state 1 to state 2, okay? So here, the one that we have is Q2 to 3. So let's look at it and see Q2 to 3. It says U3 minus U2. So it looks like that might be helpful, right? If I can solve for U3, then I can find T3. So then I look at that and I have Q, it's given, U3, it's what we need. So U2, do we have U2? I look back at my given values and I don't have it, all right? Well, actually we have R equals to A here, I forgot. Sorry. So then, well, yeah, this is good. So it means that I can go from 1 to 2, as I said, okay? I have that T1 is 300 Kelvin, so I can use that R, according to my handout, to go from 1 to 2, okay? So if I can get from 1 to 2, I can find that value of U2 to plug it into that Q, U3 minus U2. So let's see, that's what I'm gonna do. So you see that on the thing that I posted, and it says that 1 to 2, VR2 over VR1, where that is unitless, not the ratio, the VRs, all right? That's not volume or specific volume, is 1 over R, and that from the handout. And why is that true? Because that's minimum divided by maximum, and it's also equal to VR2 over VR1 because we have isentropic, okay? VR1 at 300, 621.2. We find that on A17. Make sure you are good with that. And then we can solve for VR2, all right? I solve for VR2, and I have to interpolate, all right? So there you see that I'm interpolating for T2 and for U2. And not sure why I am interpolating for T2. All right, never mind. All right, so I am interpolating first for U2. I know that because I want to use U2 and Q U3 minus U2 to find U3, okay? However, you see that I am also interpolating for T2, and that's because that will be useful to solve for pressure, okay? But that's not obvious. So I'm just going to skip that part for now. Let's say I'm just interpolating for U2 and move on to the next part. And after I interpolate for it, I solve for U3. And I use U3 to solve for T3. And what do I do with that? More interpolation. And that is one of the disadvantages of air standard. The other disadvantages are shared with cold air standard. Then I solve for T3. So again, I move from 1 to 2 using R. I found the value at U2, the value for U2, and I use the fact that Q is U3 minus U2 to solve for U3. And then with U3, I solve for T3, all right? So you guys have any questions? This is one of the things that I would ask. I guess I can't ask that right now, but if you have any questions, just please send me an email, okay? All right, so then the problem is also asking for T3, okay? Or P3, sorry, we have T3, so now we want to solve for P3. So again, we look at this, okay? And we are like, let's see, where is P3? We have PR4 over PR3 is P4 over P3. It's there, so no, it's not right because it's there, but we know it's right because we have isentropic. So sometimes we're going to use that. So watch out for that one, okay? But we also have, let's see, P2 over T2 is P3 over T3. And that one looks like the one that I'm going to use. So again, figuring out what to use for this problem or any problem is the most important part of the problem, okay? Not for any problem. Maybe some other times it's figuring out what the problem is, okay? But when the problem is already set up, what am I going to do to go from what I have to what I want, okay? So then I say, all right, P2 over T2 is P3 over T3. So is that useful? I'm solving for P3. I have T3. I don't have T2. And I don't have P2. Okay? So if you look at it, the first time that you look at it, you're like, wow, that's not helpful at all. But then the same way that we interpolate it, this is actually a really good problem because of this part over here. The same way I interpolated for U2, I can interpolate for T2. And from the ideal gas equation of state, there's a lot going on here, okay? From the ideal gas equation of state, PV divided by T is constant for any process. So I have that P1 V1 T1, divided by T1. It's P2 V2 divided by T2. And using that, I can solve for P2. If I already interpolated for T2, if I know that the ratio of those volumes is 8, V1 over V2 is 8, and I know that P1 is 95 kilopascals, okay? But again, figuring that out, not trivial at all, okay? So maybe the first one is easier. So I just want to review this here because the numbers, you know, yes, it's around 4,000 kilopascals, around 1,500 Kelvin. So those are high numbers and that matters. But how long do I have left? But what matters here is how do I attack this problem? Like, how do I find these values or how do I figure out what to use? And it was the fact that Q is U3 minus U2 to solve for that U3. And then to solve for P3, we need to figure out what equation to use. So that PR4 over PR3 equal to P4 over P3, it just, you know, for state 4, we know nothing. Okay, so we should stay away from that one. So the other one that we have, P2 over T2 equal to P3 over T3, when we look at it first, it seems that we have, let's see, 3 unknowns, okay? So we have to combine that with the fact that we can interpolate for T2 when we were solving for state 2, and that we can use ideal gas from 1 to 2 to solve for P2. So this is already solved, and in class we would have solved it as well. So I want you guys to practice this, okay? The same problem, because you're going to have something similar on your exam. Even if it's not, you know, tricky, there's just a lot going on, all right? Now, to find the thermal efficiency, that's a function of U. So that means that we need to find all our internal energy values. And it means that we need to, let's see, we have T1, T2, and T3, so we can solve for all the values of temperature there. So now we need U4. And now we are facing that problem. We have nothing at 4, it appeared. But now, okay, this problem might be too much. VR4 over VR3 is equal to V4 over V3, which is also equal to the compression ratio. Because we have T3, we can interpolate for V3 and then solve for VR4, okay? Once we have that value of VR, everything else on that row where we have VR corresponds to that state. That means that we can interpolate for U4. There is just way too much going on in this problem. And then the efficiency is 0.52, which is not that high, which is good. So, yeah. I don't know how to finish this, so it's not that bad. I'm going to post a recommended problem that you can solve 2 ways, so you can start practicing this. Otherwise, if you feel like you are comfortable with all the equations for ideal gases and for entropy for ideal gases and isentropic processes, then you are more than welcome to start practicing on Wednesday of next week. Thank you for watching, and thank you for your concern, and I'll see you guys next week.